So I believe this presentation will not raise philosophical questions like Paris, neither mind gaming questions like Jacob, but it would be actually ethical questions. Should we allow machines to do this to us or not? I'm Abubakrelsedik Karali. I'm working as a research engineer in computer vision at SICS, together with Daniel in a focus group in computer vision and pattern recognition. And I'm going to talk about one of our projects. It's about understanding human facial expressions, together with our collaborators from Stockholm University, Kansas Group, and Societar, which is a startup working in the field. Our agenda will be as follows. We will talk about problem definition, we will talk about our motivation to solve this problem, and then we will tackle the challenges and our approach to tackle these challenges. And we will show some demo and we'll conclude afterwards. And hopefully this will be in 20 minutes. So, problem definition. It's basically by definition of facial expression understanding. We are trying to train the machines to understand the facial expressions of the person we have, or the target person. So we decide the emotional state of the person, whether he is natural, smiling, disgusted, or afraid, or whatever. And why are we interested in this? Because basically, emotions are communicative. We can communicate things using emotions. And knowing this information will allow us to explore many things and will be very beneficial for us. So this is how lead us to this. This is what led us to this. We got interested in analyzing more realistic human facial expression, like in real scenarios, to understand the emotional state of the person, to further use it in several applications. It's not limited to this only. For example, you can use it for online marketing or recommendation if you are watching a video online, for example, and recording your response. You can see the response of the people here, if they are interested or not. And this can be used further to recommend more videos or more products, like if you are using a mobile app for online store or something, you are interested in an item, we can further introduce you to more items. Another application is Internet of Things. If you are in your home and you are interested in watching a movie, but you are now sleepy, and then you have a camera that can capture your facial expression, then you are lazy and sleepy. And it will dim the light for you or even turn off the TV. If you're following the technology news, you would knew about this. Uber the vehicle, the driving, well, it's a replacement of the text, I guess all of you know it, is now doing a collaboration with Effectiva, which is a startup, US startup working in the field of emotion understanding, to get a real feedback of the customers, if they are liking the ride, if they are interested in this, if they don't like it, so it's basically the automation of the like and dislike button. And one last application I would like to introduce is interviews, actually automation. This can be used as automation of the interviewing process. There's many approaches to tackle the interviewing process automation. For example, last couple of years, we have a new web server, a new website that's called Interview Streets that automate actually the process of interviewing and question and answering questions. And now we would be able, if we have this technology, to automate even the personality understanding and the confidence of the applicant. In order to reach this goal, there are some challenges, and these challenges we can summarize as follows. We don't have too much data. We have very limited data when it comes to video. It's not like the 2D cases and images cases. We also have challenges, technical challenges, like we want to detect where is the face in the stream or in the frame, and this can spans very high dimensional space, because faces can be oriented everywhere, and it might be with occlusion or something. And the last thing would be how to describe emotion if you have the face. How to describe which movement in the face actually corresponds to which emotion. So a typical pipeline to describe a solution for this would be like this. Most of the literature doing the same pipeline. First, we start with a face localization where we detect the face in the frame, and then we do a face registration where we pick the face and normalize it, normalize all the faces together to the same place, and then we extract features that can represent the expression, and finally we have classification and regression. This is mainly how it looked like back. Some pipelines use some variations. For example, if you are using automatic feature extractions like convolutional neural networks, you would fuse the last two modules together. And if you're adding other modalities like audio and text, you would add it at this step in the input. And finally, you have classification and regression. Classification if you want to design the category, to decide the category of the emotion, and regression if you want to measure the magnitude of the emotion. Mostly, the most challenging part here is the feature extraction, because, for example, you can use off-the-shelf face detector, but you need to have a very good domain experts to design good features that can describe each emotion. So most of the research is done here in the third and the fourth modules. And most of the features actually can be categorized into three categories. One is, the first one would be using the appearance of the face, like where's the eye and where's the mouth and how do they look like. And another approach would be geometric, like if you are trying to do a landmark detection or do a point detection where every point in the face is. And the last one is automatic features like convolutional neural network. Our approach, or the state of the art of technology right now, is using convolutional neural network. But the thing is, convolutional neural network in this problem, or in general, in video processing in general, is not performing as good as convolutional neural network in 2D cases. This is because of the limited data we have in videos, and when we add another dimension that's the time domain, we will end up with too much parameter, or too many parameters. So our approach at SICS to solve this problem is based on two parallel pipelines. The first one would deal with 3D convolutions. We built a 3D convolution neural network that can capture both temporal and image and 2D spatial features together with the domain expert pipeline, where we can, for example, read or detect the landmark points, and then we feed back it with our domain expert at Stockholm University, at School of Psychology. So in details, I'll go a little bit deeper in this. So the difference between 2D convolutions, if you're familiar with convolutional neural network, basically at first, or most of the layers, most of the convolution layers, you do convolution on 2D scale. So we have a filter and you have an image, and you process this image with a filter, and the results will be a 2D response map or feature map. For this case, if you did it to a video, you would lose the temporal information. Similarly, another approach to tackle this point with videos is to use a 2D filter throughout the whole video sequence for the same window. And again, it will result in a single image, but it will lose again, the temporal information, because you will lose it, because you're actually, you don't consider the temporal information respectively, you just convolve it over time. And the third approach, which we adopted, is the 3D convolutions. You have the filter, which is 2D, but in 3D we adopt it into a 3D box. And this box, we can convolve it over time. And then we will preserve the spatial and temporal information as well. So we've built our approach using this is our architecture basically. It's 8 convolution layers with 5 pooling layers and softmax after 2 fully connected layers. It was used actually for in Facebook visual understanding for activity recognition. Yeah. But still, as I told you, for 3D cases, it's not easy to get the convolution neural network to work properly or as good as image domain. So we have the curse of dimensionality. We don't have too much data, and we have too many parameters, and we have too many features, because we have a video, or we have a frame, and we have too many features that's not actually important. So we built the other pipeline, which is basically in collaboration with our collaborators from School of Psychology at Stockholm University. And it's basically to detect landmarks on the face. So we detect 86 landmarks on the face together with the gaze of the eye and the orientation of the head. It's basically based on constrained local neural field, which is, you can think about it like conditional random field, but with a layer of neural network, one single layer of neurons between the input and output layer of the CRF. And this actually to capture the nonlinearity of the data. We trained this. So yeah, the CLNF actually is 3 steps, basically. One to roughly detect where are the points of interest, and the second is to fit the appearance of these points to the trained model, and the last one is actually to regularize these points and to track it to the right place iteratively. So this is how we do our experiments. So the 3D convolution neural network is trained using the Sport 1 million dataset, which is the largest dataset available for video processing, which is labeled as well. But it is not meant to be for facial expressions. So we cannot use, for example, the last layer for classification. We have to either do fine-tuning over the last layers, or to use, for example, the output features from the last layers for another classification method, which is like logistic model trees, for example, which is performed very good with us. And for the constrained local neural field, we used the dataset of the multi-pi dataset, which is in Carnegie Mellon University. And it contained 3,000 front faces, and with variations. For the CLNF, we trained 9 base classifiers together, 9 local classifiers to detect the 86 points. And we used 86 points afterwards to find the orientation of the face using the 3D triangulation between a predefined model of the face. For facial expression right now, we have these datasets, concatenate, and we are doing experiments on it. It's very small dataset, but we are actually waiting for the dataset from our collaborators at Stockholm University. It will be very rich data, and it will be in a high dimensional frame rate and high dimensional images, I mean. This is actually the most slide I like here, because actually the fusion between, it tackles the fusion between the two models we have, the two pipelines we have. First you can think about multiple classifier system. This is basically a multiple classifier system where we can fuse the decision together. But more importantly, you can do the fusion on three levels, which is feature level, training level, and decision level. Decision level is simply using multiple classifier system technique like softmaxing the output together, or doing the average or majority vote or whatever. And the learning approach, fusion on the learning approach would be something like boosting and bagging, but it's not possible because the training of the 3D neural network, it's really complex and time-consuming. And the most interesting thing is the feature fusion. You can think about it like we train or we tell the convolutional neural network where to focus to find features, to find the descriptive features. If you consider the local, the landmark points, the 86 landmark points we detected here, you can simply do a simple feature selection test to measure which features are really important for this. And you can see here the narrow cycle or the small cycle is better. And so you can see that around eyes, eyebrows, and nose and mouth, these are the most important features for understanding emotions. While the other features out of the 86 features, it's not that important. So simply, we can mask out in the input video all of these raw features, that all of these voxel features, I mean, you can mask it out and feed just in these features. And this will drastically reduce the number of features. And at the same line, on telling the neural network where to find the features, we got a very recent publication. It's not ours. It was published from University of North Carolina. But it was exactly along the same line. It's not applied for 3D, which is our contribution will be. It's applied for 2D. So they have a 2D convolutions, 2D image, and they used actually the optical flow between two frames. And afterwards, they masked out the frame that doesn't have optical flow, or where they threshold actually the optical flow, and they masked out the pieces that has very low optical flow, and fed the rest to the neural network, and actually it learns better. This actually supports our hypothesis that we can actually affect the training of the 3D convolution neural network and tell it where to focus. So this is a small demo of what we are doing right now. I'm not sure if it will work. No? How can we? From the computer? Does it work? No? No. No, I don't think so. Does it work on your computer? No, not really. Okay, so let's try this one. Oh, that's bad. I don't know. So basically, in this demo, we have this girl. I will illustrate what's happening. We have this girl actually. This is the data from Stockholm University. This is how our dataset, our rich dataset, would look. So we have this girl, and she is actually the actor in front of her is telling her very bad stories and very sad stories, and she starts to cry. And we record this as our dataset. And here you can see the green lines, which represents the gaze of the eye, and this circle, which is the pupil size. and this rectangle represents the orientation. This implementation is done using OpenFace library and DLib library and OpenCV as well. So we can detect the 86 points, the gaze, the pupil size, and the orientation of the face. And in this, the actor actually tries to surprise this guy, and he looked shocked. But well, he's very normal here. But in the next frames, he won't be shocked. So to conclude, what we have here, so we have a room for discussions. Oh God. The project aims to understand the facial expressions and automate the process of understanding the emotional state of the actor or the target person. And we are the first to introduce actually the pupil size as a feature and the head orientation in this field, together with our collaborators from Stockholm University and the Department of Psychology. We are the first actually to tell the neural network where to focus, and it would be very interesting to actually enhance the results of the 3D convolutional neural network. And finally, we are building a massive database for this problem, which would be the first to have high-definition micro-expressions on it. And this is, thank you for listening, and this is actually one of our projects in computer vision at SICS. If you are interested in computer vision and you have problems or something, you can ask me here or ask anyone in SICS. He will lead you to the proper guy. And thank you.
Right, so we're running a little bit late on time, but we can perhaps take one or two questions. Could reinforcement learning be used to capture the time domain?
I think it would be interesting actually to test this hypothesis. I mean you can extract features from each frame and, for example, train recurrent neural network or LSTM for it. But the thing is, you would lose the spatial information over the temporal information. For example, if an eye is moving like this, the next frame, you wouldn't be able to capture this change at this position with the 2D independent features. I mean, at each frame, if you detect the features, this would be totally independent of the other frame, and you will lose some temporal information. I mean, to conclude.
All right. Okay. And I think we will have to leave the other questions up for discussion during the coffee break, which is now, and we'll reconvene at 20 to 3. Right. Thank you.
Thank you.